Likelihood function will help us understand the maximum likelihood estimation. Suppose we have m samples drawn from the unknown distribution P data. Let P model be a parametric probability distribution over the same space. The idea of the likelihood function is to tell us how likely it is for our probability distribution to have observed the samples in the dataset. The likelihood is defined as follows. We evaluate our probability distribution function for every sample in the dataset and take the product. The principle is same regardless of whether the sample space is discrete or continuous. Let's now do one example which will help us gain an intuition for the maximum likelihood estimation. Suppose our model is a normal distribution with unit variance, where mean is parameterized with mu, and we are given the following data. Let's use the likelihood function to see how likely it is for our model to have observed this data when mu equals 1.5. On the graph below, we can see these data points and the probability density function of our model with mean 1.5. For each point in the dataset, we can also see the respective values of the PDF. By taking the product of these values, we find the likelihood. Now let's compare it with the case when the mean of our model is 0. The orange probability density function corresponds to the PDF of our model when the mean is 0. If we evaluate the likelihood, we will see that it is greater than in the case with mean 1.5. It can be observed visually that the case with mean 0 has more probability mass around the data points. This can be interpreted in a way that the true distribution is more likely to have had a 0 mean than a mean of 1.5. This is the idea upon which the maximum likelihood estimation relies. The value of the parameter which results in the greatest likelihood is considered to be a better estimate. However, when the dataset is large, taking the product of many values between 0 and 1 may result in an underflow. Taking the logarithm of the likelihood will not change the argmax, but will let us convert a product into a sum. This way, an underflow is unlikely to occur.